All right. So today we're going to learn Newton's second law for rotation. This is hopefully the last of the videos for angular motion here. All right. So your learning target is here. It's pretty straightforward. Basically, you ought to be able to solve problems using Newton's second law for rotation. So the idea is in the last couple of videos we talked about rotational equilibrium. We looked at what happens when an object has a net torque of 0. All right. So this video we're going to be talking about what happens if the object does not have a net torque of 0. Okay. So really quickly to refresh your memory, what is Newton's second law? All right. Well, Newton's second law is the law that says that the net force acting on an object is equal to the mass of the object times the acceleration. Okay. I very frequently wrote it as acceleration is net force divided by mass, right? Because the acceleration depends on the force pushing the object and the mass of the object, being pushed. All right. So we're going to learn the angular or rotational counterpart for this law. All right. So as I was just saying here, everything up here in red. Let me embiggen this. Everything here in red tells us about Newton's second law, right? So the object's linear acceleration depends on the net force and the mass, right? So in English, it's that equation I just had on the board a minute ago. Acceleration is net force over mass, right? More force produces more acceleration. More mass or more inertia produces less acceleration. Okay? So it turns out that there's a similar relationship with torque. Okay? So that relationship is this. It turns out that the angular acceleration of an object is equal to the net torque divided by its inertia, but now we're talking about rotational inertia. Okay? So hopefully you're seeing that this equation here and this equation here are the same equation, except that the blue one uses angular quantities and the red one uses linear quantities. Okay? So when we learned about rotational kinetic energy, we already learned a fair amount about sort of what this I is, right? It's the rotational inertia of an object. Okay, so just as a quick reminder, remember that that rotational inertia depends on the mass of the object, it depends on the size and shape of the object, so the dimensions of the object, and the axis of rotation. Okay, and when we learned about that, I gave you these different equations for the rotational inertias. All right, and they looked like this, and you've got them on the back of your, your little honors physics toolbox equation sheet, right? So we have these ones, ones that come up fairly frequently. Well, all the ones on this page, honestly, come up fairly often. I'll call to your attention, this one here is a door, right? Because here are the hinges, and then here's the pane of the door. So, here's the doorknob, okay? But it's sort of laying flat, okay? So you could definitely tip it up on its end, and that would still be a door, okay? So, yeah, here's a wheel or like a merry-go-round, any kind of disc or cylinder. So, anyway, you've seen these before. Here's a couple others. This one comes up, well, no, not really. Why did it, there you go. So there's some more. I don't know that any of these come up very often, unless they're on the previous page. All right, and then a point particle. Really, I can't think of a situation where you'd use this for torque. All right, so Newton's second law tells us net force is mass times acceleration. The angular counterpart is net torque is rotational inertia times alpha. That's the same as what I just wrote on the board a minute ago, net torque over I, right? Algebraically, this and this are the same thing, okay? So, hopefully this makes some sense, right? The torque is what causes the object to rotate. So the more torque you apply to an object, the harder you're trying to make it turn, right? Like we talked about, providing torque to a wrench, right? Okay, so the harder you torque the wrench, the more likely it is to accelerate. But it also depends on how hard the thing is to rotate, right? Remember, the higher your rotational inertia is, the harder it is to make the object rotate, or more specifically, to change how it's rotating, right? Okay? And then so the acceleration is, dependent on those two things. All right, so probably the best way is just to dive into an example here. All right, so in this first example, we're given some information about a car. All right, and so here's what we know. The car's tires have a radius of 30 centimeters. So I'm going to use capital R to represent my radius, 30 centimeters. All right, right away I'm going to convert that to meters. All right, we know that they have an inflated mass. I'm going to use capital M of 10 kilograms. Okay, the only reason I'm using capitals is that way they jive with this. All right, the problem a little bit later here says you may treat the tire as a solid cylinder. So I copied this this equation here for our rotational inertia. Okay, so jot that down. I is 1/2 m times r squared. All right, and the question wants to know what the net torque is that we're going to need in order to get this thing to accelerate from an initial velocity of 0 to a final velocity of 60 miles per hour. Who wrote this? In a time of 6 seconds. All right. So, as is often the case, we got to deal with stupid units. So, miles per hour, if you go through and do your dimensional analysis, you will discover that this is the same as 26.8 meters per second. So, please make sure you get everything metric. All right, and we're trying to find our torque. All right, so check it out. So, at this point, we learned two equations for torque. There's the original equation that we learned, which is the force. Well, I guess I should write it the correct way, right? It's the length of the lever arm cross product with the force producing the torque, right? So technically these are vectors if you're keeping score. For us, this is just d times f times the sine of the angle, right? Because this gives us the component of the force that's perpendicular, right? Okay. So there's that. And then we've also learned this new one, which is torque is I alpha, right? So, and I guess we can assume that there's just one torque on this. So here's our net torque. So go brain. This equation here is not going to help us at all in this problem, right? But eventually we'll get to problems that use both of these. All right. But here we don't know, sort of where the wheel is being pushed to produce the torque. We don't know how much force is being applied to produce the torque. But we do know all of this information here. Okay. So let me erase some of this stuff. So we want to find our net torque. So I think it makes more sense to use this guy. So net torque is I alpha. So let's find our net torque. So in order to do that, we need to find I, we need to find alpha. So to find our I, well, it's just 1/2 mr squared. So it's 1/2, the mass was 10 kilograms. The radius is 0.3 meters. Don't forget to square it. Multiply this all out, and you get 0.45. And the units here, I can't remember if we did this before when we did rotational inertia, because usually we didn't actually have to calculate the I, right? Because usually we just cheated and used the K, right? So now we actually got to calculate this thing. All right, so you're going to get kilograms times meters squared. Kilograms times meters squared. And that's the units for rotational inertia. Okay? Now, we also got to find our alpha. Now, if you go back to the given information, most of our given information here is, linear, not angular, right? So it probably makes more sense to use this information to find regular acceleration and then use a jumper equation, right? So let's see. Acceleration is Vf minus Vi over t. So let's see, move this thing out of the way. Let's see, our Vf is 26.8 meters a second. Our Vi is 0, the time is 6 seconds. Figure this out, and you get 4.47 meters per second squared. So there's my linear acceleration. But again, I need to find my alpha. So let's go to the next page where I got a little bit more room to work. And now we can find our alpha. So alpha, our jumper equation, tells us the angular equals linear divided by radius. So 4.47 was my linear acceleration divided by our radius, which is 0.3 meters. And so you get 14.9 radians per second squared. And so now we can find our net torque. So we're going to have 0.45 kilogram meters squared times 14.9 radians per second squared. All right, so remember, so the units kind of work out a little bit magically here, and honestly explaining this requires kind of a better explanation for where this I comes from, which requires some calculus. But basically what it boils down to is one of these meters here is a conversion that converts between radius and radians. So anyway, so when you multiply this all out, you end up getting, numerically, you get pretty close to 6.7. And then the units you get are kilograms times meters per second squared, which is a Newton, but then you've got one extra meter left here. So you do get Newton meters, and if you take the time and do the dimensional analysis, you'll see that it works out, okay? Whether you make this positive or negative is somewhat arbitrary, right? I guess I would probably think of it positive because it's speeding up, but whatever. There's a little bit more information we'd need to know, okay? But so there we go. There's the net torque, all right? A lot of numbers, not super insightful, all right? So this next example, I think, maybe lends a little bit more intuition, not intuition, but it'll help you understand a little bit more what's going on here, okay? So in example 2, we've got this door. It's 60 centimeters wide, okay? So that's, again, it's a door, so it's going to be this slab shape. So the width here, weirdly, is not W. It's the width of the door, right? Because if you have a door, where here are the hinges, this is the width, and so that's going to be what we call R here, right? So our R is actually 0.60 meters, okay? 60 centimeters, right? Okay? And we know that the mass is 35 kilograms. I'm going to get rid of this little drawing down here to save some room. Okay? It says that Roy pushes the door. So what's going to happen is, so let's make a top view of this. All right, so from a top view, here's the hinge. Label it with an H for hinge. Oh, better yet, let's call it P for pivot point. Haha. Here's our pivot point. Here's the door. This distance here is 0.6 meters. Okay. And now it says Roy pushes the door. I'll do all of this in blue. Roy pushes the door 40 centimeters from the hinges with a force of 80 newtons exerted perpendicular to the door. So Roy is going to be over here, 0.4 meters away from the hinges. And he's going to push the force of Roy with a force of 80 newtons. Okay? He's producing a torque. And this 0.4 meters is important because it's the length of my lever arm. Okay? So now I've got a lever arm vector, a force vector, so I can calculate the torque that Roy is producing. So the torque from Roy is the length of my lever arm times the magnitude of Roy's force. And they're perpendicular, so I'm not even going to worry about my angles or anything, right? So let's see, my lever arm is 0.4 meters. Force of Roy is 80 newtons. Multiply this, and you get 32 newton meters. All right. Cool. So I kind of did that without even reading the problem. But so the idea is Roy is trying to cause the door to turn, right? So this is the torque that he's going to produce that causes it to turn. Okay? So now, this is the first time we've done this. That's going to cause the door to accelerate angularly this way, right? So what is that? That's, I guess technically that would be, oh, that's positive, right? So we're good. But I certainly could have made it negative, depending on how I'd drawn it, right? Now, if we assume that Roy is the only person pushing this, then this is actually my net torque, right? Okay. So it says, how long will it take the door to turn through an angle of 90 degrees? So we're looking for the amount of time that it's going to take to go through an angle of 90 degrees, which is really pi over 2 radians. Assuming it began at rest, so that means my initial angular velocity is 0. All right? So we need to find out something else. Well, check it out. Newton's second law for rotation tells us the relationship between the torque and the angular acceleration. Okay? So I know that alpha is equal to net torque over I. So I need to find I, right? Okay? So I'm totally out of room. I guess I can do it right here. So let's do this. So I, we know, is 1/3 mr squared for a door. So it's 1/3. The mass is 35 kilograms. Now R, be careful here, because R isn't the 0.4. R is the 0.6. Okay? Here's a thing that I think maybe hasn't been stressed until this point. This is super important. Remember, you guys, the rotational inertia of an object, I, is a property of the object. It has nothing to do with where the force is applied. It's a property of the object, just like mass. This pen has X amount of mass, and so X amount of inertia. Similarly, this door around this hinge has X amount of rotational inertia, dependent on the mass and where the mass is located. Okay? So, the radius of the door, the width of the door is 0.6 meters. Don't forget to square that. And so the rotational inertia ends up being 4.2, and you get kilogram meters squared. Okay? So, let's see. I'm going to clear up the board a little bit here. So, I think that we have figured out our net torque was 32 Newton meters. That means I can erase this garbage here. All right, so let's see. So now I know my net torque, I know my rotational inertia, so I can find alpha. So here we go. Alpha is net torque over I. So my net torque is 32 Newton meters. Divide that by my rotational inertia of 4.2 kilogram meters squared. And your alpha turns out to be 7.62 radians per second squared. Okay. So we are almost done. So now we know this represents how quickly the door is going to gain angular velocity as it swings through the 90 degrees. Okay? So I think the last thing we got to do is this. So now we know alpha is 7.62 radians per second squared. So now we can use all of this garbage along with our kinematics equations and find t. So I am looking at these four variables and thinking that that looks like it might help me use this equation. And since omega I is 0, this all goes away. So I am looking at pi over 2 radians equals 1/2 alpha times t squared, and solve it. Okay? And so the time turns out to be 0.642 seconds. All right? So, most of the problems that we're going to be solving here are similar to this. All right? So, here, this is a constant theme that we've run into here with problem solving. Right? With net force, we did net force equals net force, right? So we had mass times acceleration equals all of the forces added together. Right? When we did work and energy, we found that the work done by non-conservative forces is equal to the work done by non-conservative forces, right? So non-conservative force times displacement times the cosine of theta was equal to the change in total energy, right? Okay? So now our jam is going to be, I have said that's the jam a couple times here, which is already dated. And if I'm still using this video in 10 years, you're going to be like, Mr. Hecker, what are you doing? Make some new videos. All right, so anyway, so check it out. So net torque is net torque, right? So net torque is I alpha. And then assuming you've only got, well, so this is torque 1 plus torque 2 plus torque 3, etc., right? But each of these torques could be seen as the length of your lever arm times your force. lever arm times force. Lever arm times force, all right? And most of the problems we're going to solve are just going to have one force producing one torque. So really, that's going to be the deal right there. Okay? So this is how most of these problems are going to be solved. We've got two different ways to find torque. I alpha and lever arm times force. So you're going to solve those two things and set them equal to each other. All right? And solve for some missing thing. So maybe you'll be finding the alpha, maybe you'll be finding the lever arm, maybe you'll be finding the force, whatever. Okay?